It's a great pleasure to be here for this conference and to give this speak today. And I can only echo what Peter said before. Thank you very much for this amazing organization of this conference. So let me start with this. I think the whole world has understood, but maybe someone can send this slide to Donald. So the European Union promised the world that we're going to reduce carbon emissions by 80%, until 2050, and the building stock has to reduce by 90%. This basically means that the building stock has to become carbon neutral by 2050. The question is, how do we get there? And the question is, do we have answers for this? This is from my lovely hometown, Stuttgart. Compared to Hong Kong, it's rather a village, but still having 600,000 people living in the city. You see the red line, which would indicate where we have to go to get to the goal, and the blue line showing the reality. And the performance gap is getting bigger and bigger every day. So I don't want to discourage you, but I'm pretty sure we could show the same graph of many cities in the world. So the gap between what we are talking about and what we are consider as success and the reality is getting bigger. And the question is, how can we close this gap? Do we have answers how we can close this gap? And do we get lost in transformation? In Europe, Peter talked about insulating buildings. In Germany, I think we are leading the world of showing the world how we can insulate our buildings and to a certain extent, making them more ugly, but doing what we can, but as we have seen at the example of Stuttgart, not showing big success. So are we lost in transformation? Do we know the path we have to go? What we see a lot is that people put gadgets on something which is stupid to begin with. So we have to become much more smarter and create a performance by design, but we also have to become effective. And it's not only about performance. I love to show this chart. It's a picture we took from an advertisement for a spa in Tokyo where it said, "Welcome to the breathtaking Tokyo water park." And then it said, "Where you can wash away the pressure and stress of the overcrowded city." What I really like about this picture is I have no idea how much energy they use in this spa, but the energy consumption per person is negligible because people love it. People love it and people go there. So if we do a zero energy building nobody's using, it's still a waste of resources. So we cannot disconnect performance from environmental quality. We cannot connect performance from architecture quality. We have to bring it together. And this is my struggle also often with the rating systems. I think the rating systems are very important to make sure that we have a certain design excellence in the design of buildings and urban districts, etc. But they are not design tools. They do not deliver a change of how we consider things and how they do not necessarily support innovation. I think this responsibility is still up to us, to architects and engineers and also researchers, to show what innovation means and to show the innovation necessary to really close this gap between the performance, between the reality and the goals we have to achieve until 2050. Let me show you a few examples. What do we do at Transsolar and as also at the university? We call it climate engineering, climate responsive design. What does it mean? We had been invited to do an installation at the Architecture Biennale in Venice in 2010 by Secima, and we thought, what do we do? And we came up with the idea to do an indoor cloud because we said we don't want to pretend to be artists. A cloud is the visualization of climate engineering. And if you want to show a cloud, you need to have a layer of 100% humidity, and warm air goes up, cold air goes down, so we can have a bottom layer of cold, dry air and have a floating layer with 100% humidity on top of it. And to avoid that this cloud layer is touching the ceiling, we have a hot layer above. because if the cloud layer would touch the ceiling, we would get condensation and the cloud would disappear. So that was the idea. The physics is pretty straightforward and pretty simple. It took us 4 months of testing until it really worked out. And then Tetsuo Kondo from Japan designed the space and designed the ramp where people could walk and experience the different layers, the different temperature and humidity levels from below, through the cloud, and from above. Now, we are not professional cloud makers. This is not our job. This has been more like a hobby. But it shows us to what extent we can really manipulate climate and make comfortable environments where people are. So one example I want to show is from Canada, where we worked with KPMG architects already about 10 years ago on the Manitoba Hydro building in Winnipeg, a utility company from Canada. It's a Crown corporation, 100% owned by the province, with the mandate to design and build the most energy-efficient high-rise building in North America. So when we started, we analyzed the climate, and we're kind of shocked because we see 35 degrees in summer, but we see minus 35 degrees in winter. So it's freezing cold. When I arrived there for the interview, I got out, it was in January, I got out of the airport and I had to jump in a taxi right away because I thought I'm gonna die. And I said to the taxi driver, oh, this is cold here. And he said, you think it's cold? We just got a heat wave. So this gave me a pretty good impression of what this climate is about. And we studied the climate further, and we talked to people, and we found whenever it's really cold, it's always sunny. And so this is an image from Winnipeg when water is freezing instantaneously in the air. But you see this blue sky, and this is a very common condition. We looked at solar radiation. We couldn't find a single cold city in the world which has more solar radiation than Winnipeg. It has more solar radiation than the city of Milan in Italy, and it has a big majority of the solar radiation in wintertime. So we said, if there is a place on this planet to do passive solar design, it's actually in Winnipeg. And so we ended up, after a long and intense schematic design process, with this kind of twin tower with one high-rise bar facing east, another high-rise bar facing west. And there are many reasons for this kind of capital letter A shape, but what was important for us, because of the shape of the high-rise building, we got this winter garden facing south. And this winter garden helped us to really absorb and collect all the solar energy and get it into the building. So this is a section through the building. It's an 18-story tower on a 3-story podium. It's separated into three 6-story neighborhoods, we called it. So we have this 3 6-story winter gardens and below a 2-story winter garden. And what we do in winter, we get the air into the winter garden. We condition the winter garden only to 10 degrees so that the air can absorb solar energy. And then we take the air from the winter garden, humidified by a water feature, and distribute it through a raised floor plenum into the depth of the floor plate. We take it at the north side of the building, put it down into the basement, where we have a heat recovery unit that takes the heat from the exhaust air and puts it back to the supply air unit. And then in summer, when we don't need heat recovery, we exhaust naturally by this solar chimney. So warm air goes up. If we overheat the air on the way out just by exposing it to the sun, we keep this natural ventilation going even if it's warm outside. On top of it, we have almost 300 boreholes under the building, each one about 100 meters deep, to create a geothermal heat exchange. And the geothermal system is providing 100% of the cooling load for the building and about 50% of the heating load. So this is the winter garden, the 2-story winter garden in the podium on the right side, and on the left side, the 6-story winter garden. What you see is on the left side, these benches, this is where the air handling units are integrated. And behind those panels are the units which take the air from the winter garden and distribute it into the depth of the floor plate. So the reason I show this, and then on the 2-story winter garden, you see on the backside the water feature which provides humidification. The reason I show this is because this is essentially the air handling room, the mechanical room of the building. There is no additional mechanical room for air handling units in this building. It's all organized within the winter garden. What does this all mean in terms of energy? We started to compare it. So average commercial buildings in Canada have an energy consumption of plus minus, let's say, 500 kilowatt hours per square meter in a year. And the MNECB, like the code requirement when we designed this building, was 258. There was an incentive program if you are 25% better, which was at 194. And our modeling showed an energy consumption of 88 kilowatt hours per square meter in a year for this building. Now, this was the reality. So when we started operating this building, the energy consumption we metered was 100% higher than what we have modeled. And I deliberately show this because I've basically never seen a building on a bigger scale which operated properly at day one. And in 99% of all cases, nobody cares, and they continue to operate this way. We had some issues with the hydronic system, so we had to fix a couple of things. But anyway, it took us 2 years in this case. Usually, without this problem of the hydronic system, we could have fixed it certainly in 1 year. But you need to monitor, you need to optimize building operation. And after 2 years of operation, we got it to the number we have predicted. So this is the solar chimney, and let's say it makes us very proud that a piece which contributes to the operation of the building became also a piece of the landmark of the building and of downtown Winnipeg. In a very different climate, in a very different scale, we worked with Atelier Lyon from Paris on this French school in Damascus. And this French school was 100% paid, construction was paid by the Parents Association. So there was a desire to have a low-budget construction, and it had to be a low-budget construction. The fees, fortunately, and the land was paid by the French government, so it was not too embarrassing for us to work on this project. But it was very interesting because also the Parents Association came to us and asked us if we can do a building in Damascus without air conditioning, because they felt that air conditioning is making their kids sick. Which might be true if air conditioners are not well maintained. And if I look at our public buildings, even in countries like Germany, how badly they are maintained, I see a certain problem in this. So we studied the climate data of Damascus. We went there and we saw places like this. This is a souk in Damascus. They have temperatures in June, June, July, August, which are between 40 and 45 every day. But it's a dry climate, it's a desert climate. It cools down at nighttime in summer to temperatures of about 20 degrees. I find it very interesting that people life happens outside. People spend time outside, even in this 40, 45 degree environment, by having some shade, by having some air movement, and this is a souk in Damascus. And the question we ask ourselves, can we translate this into building design? And we ended up with a scheme where we have these 2-story classrooms. We have courtyards between the classroom buildings where we provide shading. We have vegetation to create a nice microclimate. And we take the air from the courtyard and pull it through ducts, which we have embedded in the ground slab, and distribute it to the bottom as well as to the upper classroom. And it's all driven by this solar chimney. So the sun hits the solar chimney, overheats the air, and drives the natural ventilation. And the backside wall of the solar chimney is a heavy masonry wall, and it's heated up by the sun during the course of the day, and it stays hot overnight. And so because it's hot overnight, it keeps the natural ventilation going, and it cools down the building over nighttime. And this is how the building looks like at nighttime. We modeled that they're going to get, at the end of a hot week, at the end of the day, they're going to get indoor temperatures of something like 30, 31 degrees. The parents said, that's perfect at 45 outside. We checked it also with adaptive comfort standards and figured out that in this hot climate, we really apply the adaptive comfort standards to this building. And The French school in Damascus, before the Civil War, they were so happy with the building that they actually wanted to extend it with the same concept, which is always a proof to us. Usually people don't call us and say, oh, what a beautiful climate in our building. So nobody walks into a space and says, oh, what a great climate here. So usually if we don't hear anything, people are happy. But it's a proof to us that it works if they want to extend it with the same strategy. Now, coming to a more humid climate in Singapore, we worked with series multiply architects from London and Singapore on this School of Design at NUS. It was designed by our Munich office, by Wolfgang Kessling in particular. And there was a vision to create a high comfort net zero energy building. So how can we create a net zero energy building in this really severe climate of of Singapore, where all year conditions are like here in summer? And we went through intense studies and figured out that a conventional approach will never get us there on this kind of 4- or 5-story building. So we looked into adaptive comfort standards, looking at the approach of using elevated airspeed to control climate conditions. And actually on Sunday I walked through Hong Kong and I went to St. Paul's Cathedral. And they used this very same approach. They have all the ceiling fans in this cathedral, and the indoor conditions, the comfort, had been really perfect. So this is a section with the different zoning we use for this building. So here's the circulation where we try to create a nice microclimate, and then there's cross ventilation through this open space. There is a full air-conditioned space for the labs. And then there's this hybrid tempered spaces, which are 26% of the floor plate with the design studios and the library, where we try to use these adaptive comfort standards to provide comfort. And then there's photovoltaic on the roof, and we extended the roof so that we really maximize the energy generation on this building. So we looked at these online tool from University of UC Berkeley. And you see that the comfort conditions we proposed at 29 degrees air temperature and 29 degrees radiant temperature would not provide a comfortable environment, so people would not be happy. But as soon as we add elevated airspeed at only 0.7 meters per second, this is not much, then we get this nicely into the comfort zone. So this was the approach. And here you see a section with all the details, let's say, with the ceiling fans that provide the elevated airspeed to provide comfort for the people. Now we did, again, all the modeling, and you see this is the power generated by photovoltaics on the building, which is about 500 megawatt hours per year. Now, if we run a conventional approach, this would be the energy consumption for this building. Then when we optimize the envelope, we get to this number. When we use high-efficient AC system, we are still using more than twice as much energy than we produce on this building. And then with the hybrid system, means with the adaptive comfort standards, we are getting close. We did 2 more iterations with more detailed energy simulation and reduced ventilation schedule to have a user demand controlled ventilation scheme in order to get this really to the number of energy generation that comes from the roof. So we see we cannot do, let's say, business as usual and just tweak it a little bit. We have to find new approaches to get to these really ambitious goals. And we are now in a process where we translate the same findings, the same ideas, together with Woha architects to the Brak University in Bangladesh. And let me jump on an urban scale. With TVK architects, we worked on Place de la République in France, and microclimate in cities have become a big issue also in Europe, and particularly in Europe, because in Europe, housing units usually don't have air conditioning. And so what we saw in the summer of 2003, when we had this incredible heat wave in Europe, statistics say that up to 40,000 people died in France due to this heat wave. And the main reason is that there was a combination of this heat wave and microclimate issues, overheating of cities, urban heat island effect, particularly in Paris. And Paris got hit the hardest. And the main problem was not the daytime, the main problem was the nighttime. The city of Paris did not cool down. Météo de France showed us some measurements, and they showed us that at nighttime, the temperature difference between downtown Paris and the suburbs had been 10 degrees. So the coolest time of downtown Paris at nighttime was 30 degrees at 6 o'clock in the morning. And you can't do nighttime cooling if the city doesn't cool down below 30 degrees. So microclimate had become a big issue and a big point of consideration in the city of Paris. And so we were really happy to work with TVK architects on the remodeling of Place de la République. You see before the remodeling, you see the dark surfaces which absorb all the solar energy over the course of the day. You see all the traffic over Place de la République and circling around Place de la République. And then here, the image after the remodeling. First of all, they took traffic out of Place de la République itself, and Place de la République is continued to the south. And the pavement is brighter so that we get more reflectivity so that the pavement doesn't heat up as much. And here you see a couple of impressions of Place de la République, and you see how people really enjoy it in hot periods and can cool down, find a place of relief. This does not solve the microclimate situation of Paris, but it's a contribution. It's one spot where people can go and find relief from hot conditions in Paris if they get hit by a heat wave. And then another climate, another scale is this urban development with Speer and Partners architects from Frankfurt for Abuja in Nigeria. And again, climate responsive design has not only to do with building design, it has a lot to do and even more with urban design. The city of Siena claims that they have a negative urban heat island effect, that the temperature in downtown Siena during daytime is lower than the temperature in the suburbs. This has been achieved by density, by urban form, and the reflectivity of material, only by architecture, by urban design of the city. So we see how much impact massing strategies and the use of material has on urban climate and microclimate outdoor comfort for people. So we developed a strategy to create a self-sustaining energy efficient city of the future. So coming back to this question of resilience infrastructure, it has also, if we provide more energy generation within the city, we create also a more resilient infrastructure. And so we came up with this strategy that first we have to think about the optimized city layout in context, what I have mentioned before, and then talk about how we minimize energy consumption in buildings, and then talking about the energy efficiency of energy generation. And finally, at the end, talking about how we can maximize the use of renewable energy. And so this is the site from the mountain, beautiful site. And this is the climate. We see that all over the year, the temperature is between 20 and 40 degrees. We see in summer, it's less hot. We get only daytime temperatures of about 30, but this is also when it's most humid. It's a very humid environment, particularly in summer. And so this is just an image showing when we started to analyze massing strategies and how we can minimize solar exposure in the public realm, and then looking at wind and how we can introduce wind into the city so that we create air movement and nice outdoor comfort conditions. Here, a couple of strategies, calculations on how we can optimize the time when we have comfortable condition and minimize heat stress in public realm. Here, some guidelines on the building design in step 2, and it's not rocket science. I mean, this is very straightforward. We are talking about overhangs to provide shading. We are talking about the depth of a floor plate so that we get access to light. I mean, this is something which really drives me crazy. We always talk about environmental quality. We talk about energy efficiency. Using daylight is very energy efficient. There's no transformation. We use daylight, use the sun, what it provides to us. At the same time, we built floor plates where 50% of the workstations are disconnected from daylight. I mean, this does not make any sense. So we provided these design guidelines, and then we looked at different ways of energy generation. We ended up with a proposal with tri-generation, where we use like cogeneration, running an absorption chiller and providing district cooling. And then here you see the 4 steps. Then we get with the adding renewable energy on the roofs of the building, using solar panels on the roof of the building. We reduce total energy consumption by 96% for the whole city. So this is all not rocket science. It's just straightforward design. And what struck me, and the reason I show it, is because of this diagram. We looked at the economics of all of this, and we found that the return of investment is less than 5.5 years for the whole system. And so this raises the question, why don't we do it everywhere? But it also, we achieved this 5.5 years only because we optimized already the city layout, we optimized already the buildings. We have to reduce the load on we put on our infrastructure. So we have to optimize the buildings first. If we reduce energy consumption, we worked on Master City. Master City showed us that if we reduce energy consumption of our buildings by something like 60 to 80%, we can provide 100% energy on the basis of renewable energy sources for the same price a conventional infrastructure would cost for conventional buildings. So we have to do it all, and then we can also become very economical. So this brings me to the end. And just to summarize, I think we have to be successful on all scales. It doesn't help us if we are just successful on a unit scale, or just successful on a building scale, or only successful on an infrastructure scale. The Abuja project showed us that we have to be successful on all scales to really succeed, and we have to be holistic and synergetic. And then, very important, it's also about architecture and environmental quality. We have to create delight. We cannot convince people to suffer. We have to show them that we can provide a better environment using these kind of technologies and strategies. And we have to be more aspirational, and we have to be more inspirational with what we do. And with this, I come to my last slide. I didn't want to talk about politics, but I saw this picture, I saw this slide at a bar in Hong Kong, and I had to make a picture out of it because I thought this is great. Thank you very much.